Hello my dear students, welcome back to your channel. Hope you all are doing well. Today with this video I will try to cover all important points and formulas of chapter 14, that is semiconductor electronics. In this chapter different topics to be covered are: first, energy bands in conductors, semiconductors and insulators, then semiconductor diode, or you can say PN junction diode, after that IV characteristics and forward and reverse bias, then diode as a rectifier, at last special purpose PN junction diodes like LED, photodiode and solar cell. So first let us start with chapter name. What do you mean by semiconductor electronic devices? What is this electronic devices? Electronic device, actually it is a branch of science which deals with controlled flow of electrons through vacuum, gas or semiconductor. In the previous days we use vacuum tubes, but nowadays semiconductor electronic devices are used. Why these semiconductor electronic devices are used? Because it is very small in size, it has low power consumption, also it has long life, and also it has low operating voltage. That's why nowadays basically semiconductor electronic devices are used. Now next, classification of solids on the basis of conductivity. On the basis of conductivity, solids are divided into three types: conductor, insulator and semiconductor. Conductor are those substances through which electricity can pass easily. It means it has very high conductivity and very low resistivity. For example, metals. Insulator are those substances through which electricity cannot pass. For example, wood, rubber, it has very high resistivity and very low conductivity. And last, semiconductor, third type, is very important, and which is the main discussion of this chapter. Semiconductors are those substances whose conductivity lies between conductors and insulators. For example, germanium, silicon, carbon, all these are semiconductor which has 4 electrons in the outermost shell. Now these are classification of solids on the basis of conductivity. Next, there are different types of semiconductors. First one is elemental semiconductor and then compound semiconductor. What is this elemental semiconductor? Elemental semiconductors are available in natural form, that is pure form. For example, silicon, germanium, etc. Next, compound semiconductor. These are made by compounding 2 or more metals. For example, CDAs, GAAs, gallium arsenic, CDSE, all these are compound semiconductors. Now after this, I am going to discuss energy bands of solid. What do you mean by this energy band? Actually, what happens in a crystal, due to interatomic interaction, valence electrons of one atom are shared by more than one atom in a crystal. Now what happens when these valence electrons of different atoms combined together? There is splitting of energy level takes place, and this collection of closely spaced energy levels are called energy band, right? Now in this energy band there is a valence band, conduction band, forbidden energy gap. What is this? First, valence band. Valence band are energy band which includes energy levels of the valence electrons. This energy band contains valence electrons, and this band may be partially or completely filled with electrons. What do you mean by conduction band? Conduction band is the energy band above the valence band and it contains conduction electrons. This band is empty or partially filled with electrons. Now after this, energy band gap. What is this energy band gap? Energy band gap is minimum energy required for shifting of electrons from valence band to conduction band for conduction process, right? And then Fermi energy, it is maximum possible energy possessed by free electrons of material at absolute 0 degree temperature. So this one is energy band diagram. This is the nucleus, then different valence electrons combined together, the difference levels of these valence electrons in this way: first band, second band, and then valence band is formed. In this valence band, valence electrons are present. These may be partially filled or fully filled, right? And this conduction band consists of conduction electrons. It may be partially filled or empty, and there is a gap between this valence band and conduction band. The gap is called forbidden energy gap, and this electrons in the valence band requires this amount of forbidden energy gap to move from this valence band to conduction band for conductivity. So this much energy is required to move an electron from valence band to conduction band, then only conduction takes place. So this is energy band diagram. After this, on the basis of this energy band diagram, solids are divided into metals, semiconductors and insulators. What is this metals? In case of metals, this valence band and conduction band overlap. So there is no energy gap between valence band and conduction band, and electrons easily move from this valence band to conduction band. In case of semiconductors, there is a small energy gap between this valence band and conduction band, so that at 0 degree temperature there is very few electrons in the conduction band and little bit conductivity is there. But when you increase the temperature, these valence electrons move from this valence band to conduction band, conductivity increases. In case of this insulator, there is a large band gap between valence band and conduction band, so there is no conductivity in case of insulators. It has very high resistivity, and this is Fermi energy level. After this, there is a difference between conductor, insulator and semiconductors on the basis of energy band diagram. Here in case of conductors, valence and conduction bands overlap, energy gap is 0, it has very high conductivity. Valence band and conduction band are partially filled. In case of semiconductors, at 0, electrons in valence band do not have sufficient energy to jump to conduction band, so it behaves like an insulator at 0 degree Kelvin. But it has very small energy gap. So when you increase the temperature, its electrons from valence band jump to the conduction band, and its conductivity lies between conductors and insulators. In case of insulators, valence band is completely filled with electrons and conduction band is empty. So valence and conduction band have very large energy gap. So its conductivity is very low and resistivity is very high. So these are difference between electrons, conductor, insulator and semiconductor on the basis of energy band diagram. After this, I am going to discuss classification of semiconductors on the basis of purity. There are two types of semiconductor. One is intrinsic, another one is extrinsic semiconductor. Intrinsic semiconductors, those semiconductors which exist in pure form, pure state. And in case of intrinsic semiconductor, charge carriers are mainly electrons and holes, and number of electrons and holes are equal in case of intrinsic semiconductor. Both number density are same. It is equal to Ni. Ni is intrinsic carrier concentration. Actually, intrinsic semiconductor at 0 degree Kelvin, it behaves like an insulator. But we increase the temperature, there are some thermogenerator electron pairs, and hence it conducts current. This germanium, silicon, all these are intrinsic semiconductor. It has 4 electrons in the outermost shell, which are covalently bonded with the neighboring semiconductor atoms, right? Like for example, germanium, it has 4 electrons in the outermost shell. These are covalently bonded with the neighboring 4 germanium atoms. In this way, all in case of intrinsic semiconductor, all are covalently bonded with each other. Hence, it has 0 conductivity at 0 degree Kelvin. But when we increase the temperature, these bonds breaks and conductivity increases. What is this extrinsic semiconductor? To increase the conductivity of intrinsic semiconductor, because at 0 degree Kelvin it behaves like an insulator. So to increase its conductivity, some doping is there. So a semiconductor doped with suitable impurity to increase its conductivity, that semiconductor are called extrinsic semiconductor. And on the basis of doped impurity, what type of impurity were added? These are of 2 types. One is N-type semiconductors, another one is P-type semiconductors. So first I am going to discuss about N-type semiconductor, then after that P-type semiconductor. What is this N-type semiconductor? In N-type semiconductor, when a small amount of pentavalent impurity atom is added to a pure semiconductor, then it provides large number of free electrons, and this extrinsic semiconductor formed as known as N-type semiconductors. And in this N-type semiconductors, majority charge carriers are electrons and minority charge carriers are holes, and number of electrons is greater than number of holes. Why? Suppose this is a pure semiconductor. In this one, some pentavalent plus 5 valence electron impurity atoms are added. So these 4 valence electrons forms bond with the neighboring 4 silicon atoms, or you can say germanium atoms, but this 5th electron is free. These unbonded free electrons donated by pentavalent atom. So it has large number of electrons as compared to holes. Holes are nothing but vacancy created by the electron are called holes. These are positive charge. So the conduction in N-type semiconductor is because of this free electron donated by this pentavalent impurity atoms. Hence this pentavalent impurity atom donates electrons, that's why it is called donor atom. Pentavalent impurity atom are called donor atom because it donates extra electrons, right? So this is n-type semiconductor. Here important point is majority charge carriers are electrons and holes are present in small amount. These are minority charge. So number of electrons is greater than number of holes, right? This is energy diagram of n-type semiconductor. This one is valence band, above which conduction band is present. This one is energy gap. So here large number of electrons are present below the conduction band. So this one is Fermi level and this is extra electrons energy levels are there. So this is diagram of n-type semiconductor. After this, next one is p-type semiconductor. In case of p-type semiconductor, here trivalent impurity is added to a pure semiconductor. As a result, large number of holes are created in it. Suppose this is pure semiconductor. In this one, gallium or any trivalent impurity atom is added. So these three electrons form bonds with the neighboring this in semiconductor or germanium atoms, and this fourth one is free. This one is holes. So this large number of holes are provided in this semiconductor by the addition of this trivalent impurity atoms like gallium, indium, such type of impurity atoms which provides holes or which accepts electrons. Holes are positive charge, so it accepts electrons. That's why these trivalent impurity atoms are also called acceptor impurity atoms. Why? Because it accepts electrons, right? So this is p-type semiconductors, and important point is in p-type semiconductor majority charge carriers are holes and minority charge carriers are electrons. That's why number of holes is greater than number of electrons in case of p-type semiconductor. And next is energy band diagram of this p-type semiconductor. This one is valence band, above which conduction band is present. Here large number of holes are present above the valence band. This one is Fermi level and this is extra hole energy levels. So in this way you draw energy band diagram of p-type semiconductor. This one is for p-type and the one is for n-type semiconductor. In n-type semiconductor, donor energy level below the conduction band. In p-type semiconductor, acceptor because holes accept electrons. So this one is called acceptor energy level above the valence band. In this way, you draw energy level diagram of p and n-type semiconductor. In n-type semiconductor, number of electrons is greater than number of holes, and in p-type semiconductor, number of holes is greater than number of electrons. Electrical conductivity in case of extrinsic semiconductor is given by sigma equal to E Ne mu E plus Nh mu H, where rho is resistivity, mu E and mu H are what? Mu E and mu H are mobility of electrons and holes. We note one point, energy gap for germanium is 0.72 electron volt and energy gap for silicon is 1.1 electron volt. So these are about different types of semiconductor. What are p-type semiconductor, what are n-type semiconductor. Now after this, next is p-n junction. Now what is this p-n junction? How this p-n junction is formed? It is an arrangement made by a close contact of n-type semiconductor and p-type semiconductor. When n-type semiconductor is placed in contact with a p-type semiconductor, then the p-n junction is formed. Now how this p-n junction is formed? What are different process takes place during p-n junction formation? So you know, in case of p-type semiconductor, majority charge carriers are holes. And in case of n-type semiconductor, majority charge carriers are electrons like this one. I think diagram is clear to all of you. This side is p-type semiconductor and this side is n-type semiconductor. Now what happens due to concentration gradient, electrons diffuses from this n side to p side. Electron starts diffusing and holes diffuses from this p side to n side, right? Now after this diffusion of majority carriers, what happens? Potential, this side negative charge is left, this side positive charge is left. So potential difference is created near the junction, and this junction or layer is called depletion layer, depression region. Because why it is called depression region? Because it is free from mobile charge carriers. Now this potential difference setups internal electric field from which direction to which direction? This one is positive and this one is negative from N to P side. Internal field is created, and this potential difference across this depletion layer acts as a potential barrier. That's why it is also called potential barrier or depletion layer potential. That's why it is also called barrier potential. This potential difference is also called barrier potential because it further opposes diffusion of electrons and holes from N and P types, right? Now, after diffusion process, what happened? Potential barrier is formed. Then there is drift of minority carriers. What is minority carrier in case of P type semiconductor? Yes, electrons. So electrons start drifting from P type semiconductor and holes start drifting from N type semiconductor, and drifting of minority charge carrier takes place, and this way drift current is produced. So different process involved during PN junction formation is, first one is diffusion of majority carriers, diffusion, then potential barrier formation is there, and at last after this drift of minority charge carrier takes place. So this is how PN junction formation takes place. You must draw neat and clean diagram. Electron drifts from this N side, electron diffuse from this N side, holes diffuse from this P side. After the potential barrier is formed, this further opposes diffusion of electrons and holes, and hence it acts like a potential barrier. Then after that, drift of minority carrier takes place, electrons from this P side and holes from this N side. So in this way PN junction formation takes place, and this is the symbol of PN junction formation. Now after this, semiconductor diode and PN junction diode. This PN junction can be used as a PN junction diode or semiconductor diode. What is this PN junction diode? A semiconductor diode is basically a PN junction with metallic contacts provided at the ends. Here this is a symbol of PN junction, like this one. This is the symbol of PN junction. This side P and this side N. And when you connect these two P and N sides by a metallic contact, then PN junction diode is formed. With the help of these metallic contacts, potential difference is applied across this one, and this way two types of biasing is done. One is called forward biasing, another one is called reverse biasing. So what is this biasing? Biasing is nothing but application of this external voltage to a PN junction diode. This is called biasing, and biasing is of two types. One is forward bias, another one is reverse bias. Now I am going to discuss these two types of biasing. First, forward bias. What is this forward bias? This is PN junction. Right now, if the P side is connected to this is external biasing. Battery is connected to this one. If P side is connected to positive terminal of the battery and N side is connected to negative terminal of the battery, then this type of biasing is called forward biasing. And under this biasing, what happens? This potential difference is from this side to this side, and this external potential difference is from this side to this side. So this is opposite to the potential barrier. Hence what happened? This effective potential barrier decreases, and hence this width of the depletion layer decreases in case of this one, and it offers very low resistance and large forward current flows due to majority carriers in case of forward bias. So in case of forward biasing, a large forward current flows due to majority carriers. Why? Because the width of the depletion decreases in case of forward bias. Next one is reverse biasing. In reverse biasing, what happens? This P side is connected to negative terminal of the battery, opposite that of forward bias, and N side is connected to this N side is connected to positive terminal of the battery, and P is negative terminal. Now in this one, what happened? This voltage is in this direction, external voltage also in this direction, so both are in the same direction. Hence this potential width increases here. This width of the depletion layer increases, and hence reverse current flows due to minority charge carriers only, and there is very small amount of reverse current is produced in case of reverse biasing. So to increase the current, we always connect in forward biasing, and if you want to know current flows in the circuit, you have to do reverse biasing. In case of forward biasing, large amount of current flows. In case of reverse biasing, small amount or no current flows. So this is forward and reverse bias, and this one is the IV characteristics of forward and reverse biasing. This one is forward voltage, this side reverse voltage. Now in forward voltage, forward biasing, what happens? current starts increasing and large amount of current, forward current flows in case of forward biasing. This is forward region. In case of reverse biasing, no current flows, current nearly about zero, and at last suddenly large amount of current flows. This region is called breakdown. This voltage is called breakdown voltage, at which large amount of current flows suddenly, and this is reverse region. So in this way you draw IV characteristics of PN junction diode, right? Hope it's clear to all of you. Now this PN junction diode can be used in different ways, right? It is used as a rectifier also, so which is very important, rectifier. Then Zener diode, it is also used as a photodiode, light emitting diode, etc. So Zener diode is not in your syllabus for this year, but I'm going to discuss about rectifier in detail, then photodiode, light emitting diode, and solar cell. So next one is rectifier. What is this rectifier, right? Rectifier is a device which converts alternating current of voltage into direct current of voltage, right? The process of converting this alternating current into this direct current is called rectification. So rectifier is used to convert AC into DC, and for this purpose junction diode is used. So diode is used as a rectifier. There are two ways of using diode as a rectifier. One is half wave rectifier, another one is full wave rectifier. And on which principle this rectifier works? It's working based on the principle that junction diode offer very low resistance in case of forward bias and very high resistance in case of reverse bias. So what happens? When the circuit is in forward bias, it offers very low resistance and current flows through it. But when it is in reverse bias, it offers very high resistance and no current flows through it. So this property, unidirectional property of diode, unidirectional property of diode is used as a rectifier. It means to convert AC into DC. So first, what is this half wave rectifier? Half wave rectifier means it converts the half cycle of applied AC into DC signal, and for this one ordinary transformer is used. This is the circuit diagram of half wave rectifier. This one is the transformer, primary of the transformer, secondary of the transformer, right? Here AC input signal is given to the primary transformer, and here PN junction diode is used. Only one diode is used in case of half wave rectifier, and output is obtained across this one and this end of the secondary of the transformer. Now what happens during the positive half cycle? This end becomes positive and this end becomes negative. So the diode is in forward bias during the positive half cycle. This is input AC is there. This is the positive half cycle. During this one, this diode is in forward bias, and in case of forward bias, it offers very low resistance, it conducts current. So output is obtained across the first half cycle. Now during negative half cycle, what happens? This end is negative and this end becomes positive. Negative means this P is connected to negative, it means reverse bias, and it offers very high resistance and no current flows through it. So during negative half cycle, no current flows through it, current is zero. Then again during the next positive half cycle, it conducts current because it is in forward bias. Then in next negative cycle, it is in reverse bias, no current flows. In this way, unidirectional current is obtained and this AC is converted into DC, but only half positive half cycle is converted. In the negative half cycle, no current flows. That's why it is called half wave rectifier. It only rectifies half of the input into DC, right? Now next one is full wave rectifier. In case of full wave rectifier, the whole cycle of applied AC signal is converted into DC signal, and for this one central tap transformer is used here. This is the central tap transformer. Here two diodes are used, two PN junction diodes are used. In this way both cycles are converted into DC. What happened during the positive half cycle? This end becomes positive and this end becomes negative. So this diode D1 becomes positive and D2 becomes negative. So only D1 conducts current and D2, it is in reverse bias, no conduction takes place through D2. So during the positive half cycle, D1 current is due to only D1. Now during the negative half cycle, this end becomes negative and this end becomes positive. So this D2 is in forward bias. So only D2 conducts and D1 is in reverse. D1 does not conduct. So during the negative half cycle, only D2 conducts. In the same way, next positive half cycle, D1 conducts. Then next negative half cycle, D2 conducts. In this way, both half cycle we get unidirectional current flow due to these two diodes, right? So here both cycles are rectified into DC signal. So that's why it is called full wave rectifier. Here whole cycle of applied AC input is converted into DC signal. Here two diodes are used. So at one time only one diode is in forward bias, other diode is in reverse bias. So in this way both cycles are converted into DC signal. So this is full wave rectifier. After this, there are many other applications of PN junction diode. These are used in optoelectronic device. What is this optoelectronic device? These are semiconductor diodes in which carriers are generated by photons, that is photoexcitation. Such devices are known as optoelectronic devices. And I am going to discuss three optoelectronic devices, that is light emitting diode, after this photodiode, and then solar cell. So first one is light emitting diode. What is this light emitting diode? These all three are very important for short marks question, right? So first, light emitting diode. It is a heavily doped PN junction diode which converts electrical energy into light energy. It is always operated in forward biasing. It is forward biased PN junction diode which emits light when recombination of electrons and holes takes place at the junction. At the junction, what happens? Suppose this is a diode, right? And it is operated under forward biasing where P is connected to positive terminal and is connected to negative terminal of the battery. Forward biasing is there. Not what happens? Due to this forward biasing, more number of electrons moves from N to P side and holes from P to N side. Then there is recombination of these majority carriers with the minority carriers at the junction takes place, and hence energy is released in the form of heat. So if the semiconductor material PN junction is transparent to light, the light is emitting and the junction becomes a light source. That's why it is called light emitting diode. The color of the light depends upon the types of material used in making the semiconductor diode. Like if gallium arsenide is used, then light is emitted in the region infrared region. Gallium phosphide, then red or green light is produced. Gallium arsenide or phosphide, then yellow, red or yellow light is produced. And this is the symbol of light emitting diode. This one is operated under this forward biasing right now, and here light is emitted and near the junction. So important thing is that in case of light emitting diode, it is operated under forward bias, and due to forward bias, recombination of electrons and holes takes place at the junction. Light is emitted in the form of heat and light near the junction, right? This is the symbol of this light emitting diode, and this one is the IV characteristics of this light emitting diode. Different colors of light is emitted near the junction when voltage, this side voltage is there and this side current in milliampere is there, forward current is there. So different color of light is emitted near the junction in case of LED, right? Now one important thing in this case is LEDs has the following advantages over this incandescent low power lamp. What are different advantages? It has very fast action, no warm up time is required. It is nearly monochromatic. Light emitted is nearly monochromatic. It operates under low voltage, low operation voltage, and less power consumption is there. Fast on off switching capability. It has very long life. These are advantages of this LED over conventional incandescent low power lamp, and this is very, very important, right? After this, next device based on PN junction diode is photodiode. What is this photodiode? Photodiode is actually a special type of junction diode which is used for detecting optical signal. This part is very, very important. This photodiode is used for detecting optical signals, and it is operated under reversed bias PN junction. It is also very, very important point. It is made from a photosensitive material, right? This is the circuit diagram of photodiode. This is a PN junction. It is connected in reverse biasing condition. This P is connected to negative terminal of the battery and is connected to positive terminal of the, it means reverse biasing is there. Not what happens when the light of suitable frequency falls over this near the PN junction, then electron hole pairs are generated near this p-n junction. Suppose this incident light has energy h nu, and if it is greater than the band gap falls on it, then electron holes pair will be generated near the junction. This is near the junction, electron holes pair generated. Now this electron holes pair has its electric field of its own. Now under the application of this electric field, electron hole pair will be drifted towards the direction of electric field. It means electron moves towards n side and holes move towards p side. Now n region has already more number of electrons. Some extra electrons are moving in n region. So there is an EMF between this n side to p side increases. And when external voltage load is connected, what happens? Photoelectric current flows, and this way photovoltage is produced. So this is used for detecting optical signal, and this is the circuit diagram. This one is symbol. This is p-n junction, and light is incident near the junction, and this one is the IV characteristics of photodiode. Here it is operated under reverse condition. So this reverse voltage is there, and this side, if intensity I1, this light graph is like this one. If you increase the intensity of the light, I2 the graph is like this one, in this way at different intensities. This I4 is greater than I3. I3 is greater than I2 and I2 is greater than I1. So if you increase the intensity of light, the graph is like this one. This is the IV characteristics of photodiode. So in this way, you have to write 2 or 3 main points that it is used for detecting optical signal. It is operated under reverse bias condition. This IV characteristic is diagram, and this one is the symbol. Here from this figure we observe that current in photodiode changes with change in light intensity, and when reverse bias is applied, the current changes with the change in intensity of light. Right? Now after this, last important application is solar cell. What is this solar cell? Solar cell is actually a p-n junction diode which converts solar energy into electrical energy. The material used for the solar cell are silicon and gallium arsenide. This is a symbol for solar cell. Now here n-type and p-type semiconductor is used. N-type semiconductor is placed over p-type semiconductor, and n-type semiconductor, it is very thin, so that light enters from this n-type semiconductor to near the junction. Now how it works? When light of energy greater than the band gap, then what happens? Generation of electron hole pairs takes place near the junction. Now near the junction, electron hole pair are generated, and due to this internal this electric field near the junction, electron moves towards the n side and holes move towards the p side. Now what happened? First generation of electron holes pair takes place, then separation of electron holes takes place. Electron move towards n side and holes move towards p side. Now these electrons are collected by the front side, and these holes are connected by the back contact. Now front surface has all electrons are there, and from back surface holes are there. In this way, potential difference is created like this one. Holes is at the top surface, holes is at the back contact, and electrons are collected at the top surface. The top surface has negative voltage and bottom surface is positive voltage. In this way, photovoltage is created this side, and when external load is connected to this one, photocurrent flows through this one. So this is the working of solar cell, right? And this one is the IV characteristics of solar cell, and this one is symbol. Here light is incident on this front surface of the p-n junction diode, right? And due to this light, generation of electron hole pair takes, and the separation of electron hole pair takes place. Electron move towards n side, holes move towards p side, and potential difference is created near the junction. And when it is connected to external load, photocurrent flows. This is IV characteristics of photodiode, right? And this side V, this side R, and this side is the open circuit, and this one is for closed circuit. You must remember this diagram. And the material separator for solar cell must have high. Which type of material is used for solar cell? Those material which have high optical absorption capacity. Optical absorption capacity, and also which has band gap in the relation between 1 to 1.8 electron volt. These types of materials are used. Also those materials which are very high conductivity and low cost is also very low. So these are about solar cell, which is used to convert solar energy into electrical energy. And these are all about quick revision of this chapter 14, semiconductor electrons. Hope it's clear to all of you. So with this, I am going to end my class. Hope you like this quick revision series of class 12 physics. If you liked it, then don't forget to subscribe my channel. Okay students, keep revising and stay tuned with this channel. Thank you.